Again, thank you all again for coming and to this last fourth of the four talks. And we have Hayley Grape, who will talk about meeting in the middle, choosing a typical map from Congressional Redistricting Maps. Hayley, the floor is yours.
Oh, I was on mute. Okay. So hi, my name is Haley. I'm currently a junior right now, and I'm actually studying abroad. So it is 9:30 right now. And I'm a computer science and economics major. And this past summer, I worked with Professor Brian Bruback and PhD candidate Syed Esmaili at the University of Maryland on a project involving redistricting and gerrymandering. Um, just as an overview of redistricting in the US, we have a representative democracy, just meaning that we elect local leaders to represent us on our interests on a national level. And this is done by dividing up states into congressional districts based on population. So every year that the census comes out, so like every 10 years, they need to redraw the districts to accommodate for that population change. Um, oops. Okay, yeah, next one. And the problem with this is districts are often drawn by the state legislators themselves. So if I say majority Republican if there's a majority Republican state legislature, the Republicans are in charge of drawing the maps. And as you can kind of tell, the system can lead to a lot of failures. And but I would like to mention that some states are beginning to set up independent redistricting commissions, but often it is the state legislature that has the final say in terms of like what they do. So because of the perverse incentives in this state of the nation, this often means that POC voices and entire communities are silenced by the way the government draws the districts. So they can either like pack them all together or break the community apart by dispersing them throughout many other districts. And a lot of the districts drawn are very highly partisan and favors the current party in power. So here we can kind of see like an example of what I'm talking about. So this is like just a simple 40-60 split of yellow, blue, let's call Democrats, yellow, let's call Republicans. And but we can see up here, I don't know, can you see my mouse? I don't know if that works. Okay. So up here we can see that these are the disproportionate ones. So in here, we have the Democrats winning all the districts, even though there are still 40% Republican, or over here where the Republicans actually win, even though that there is a majority Democrat. Yeah. So then if we look at the right-hand side, we can see like a real life example of this. So this is Maryland's third congressional district, and it's often called like the praying mantis district because of the way it's just really oddly shaped. And we can kind of see that it's very much like not contiguous, and it goes almost out of its way to avoid certain areas in Maryland. So before I jump into our research, just to talk a little bit about the related research that's kind of been done is so far there have been like several papers trying to establish a criteria for determining if a state is gerrymandered or not. And so these formulas that they've devised have even been used in like Supreme Court arguments for like arguing that a state has gerrymandered their constituency. Or there's other research that tries to optimize a certain quality of a redistricting plan. So for example, compactness. This is one of the more sought out qualities, and it disregards basically any partisan information of the constituents themselves and just tries to keep the communities packed together. And then we also have ways that try to optimize having competitive districts, meaning that they want to draw the districts in a way so that there's narrow margins between the two parties. So now getting more so into our research is the question the heart of our research is how do we choose a redistricting plan given that there's multiple ways to draw districts. We saw before that there's multiple ways and everything like that. And the previous research, as I highlighted, kind of just tries to either focus on like a specific quality of a map, or they just try to determine whether a state has been gerrymandered or not. Yeah, so that's kind of what I said. So just as a general outline, first it's just going to go through how we created like this set of like generated maps. And then we converted each map to a metric space, and then what like the centroid is and what we mean by typical map, and then our test results. I know I spelled test wrong so far. Okay, so first, to generate the maps, we did use an open source tool called Gerrychain, which takes a starting point for a map and generates a set of maps using Markov Chain Monte Carlo. Or in simpler terms, it just forms new redistricting plans in like steps. So basically, we use specifically something called recombination, or recom for short. And in this process, at every step, it randomly merges two districts together and then splits them up. And it uses metrics of like fairness, like I said before, like equal population size, contiguity, good shape, to test whether that map that's currently being generated is getting better. And then the theory here is that after enough steps, it should converge to a random redistricting plan. So for example, so you take the original map of like the state and its congressional districts. And so if you just run it for one step, it's gonna look pretty similar to the original one. But if we run this chain for enough times for enough steps, it should look a lot different, and each new map that has been generated should look still a lot different than the original one, and it should be getting more random. So here we have kind of like a little GIF of the recombination process, if none of what I said earlier makes any sense, which is completely understandable. So kind of just waiting for this kind of restart. I know it's going pretty fast, but especially at the beginning, we can see the process of the merging districts and then splitting. Yeah, so right there. And we can see how they're being merged together and then split apart. And we can even see that the more this runs and the more it moves is like another chain. The more it runs, the more random the districts get. And so next is our choice of metric space. So each map that we generate comes with a VTD, which just stands for voter tabulation district. This data contains like thousands of entries, and each entry represents between like 0 to 2,000 people who all lie within the same district. And each entry is numbered with like an ID as well, as like a unique identifier. And so in order to find the most typical map, we needed a way to represent this kind of abstract map that's like computable. So we utilize a binary system where if two VTD entries are in the same district, there should be a 1 in their corresponding row or column. So here's a better example that kind of simplifies it more. So we can see that VTD entry 1 is in district 1, VTD entry 2 is in district 2, and VTD entry 3 is in district 1 again. So if we look at row 1, column 3, we can see that there's a 1. If we look at row 3, column 1, we can see that there's a 1. But since 1 and 2 aren't in the same district, if I go to row 1, column 2, we can see that there's a 0. We also needed a way to measure the distance, so how far away one map is to another. So we have this equation, which basically just represents how many entries you would have to, how many times you would have to delete and add to transform one map into another. So at like a higher level overview, we can understand that two maps should be like nearby if most of the pairs of VTDs are in the same district of one map and they're also in the same district as the other one. And so since we're using binary numbers, this also works for the inverse. So that the pairs of VTDs that are not in the same district for one of the maps should, if they're similar, for the other map should also be the same and not in the same district as well. So again, if none of that made any sense, here's kind of a better representation. So We can see here that we have the matrix that I had before, or the 2D vector that I had before. And so this one is pretty close. So the only difference is these two, which when I talked about adding or deleting, we would basically just have to add these two to make these the same district, to make these the same map. But we can see over here that these two are not particularly close. We would have to delete like 4 entries in order to get them to look approximately the same. Also, I just want to note, it doesn't seem like a lot, but this is on like a 3x3 because I didn't want to overcomplicate. But in our actual research, we did use like 10,000 by 10,000 matrices. So yeah. And then we also did use weighted distance, which basically, since each VTD entry has a population assigned to it, we can use like a 1D population vector to multiply the binary inputs. And then so we also have the centroid. So this is, so once we have all the matrices mapped to our metric space, we can easily compute what the median is by just taking all the inputs and then dividing it by the total amount of maps. And so once we have this, which we call like the median, we can iterate through the maps again and use that distance metric that I showed before to find the map that is the closest to the middle that we calculated. And so yeah, this is what we call the most typical map out of the generated set. And so we actually did tests on this. And so our results, so going back to, I guess, our outline of it, how we generate our set of maps, we generated 50,000 maps for the state of Pennsylvania. And using the converging principle, we burned in, which just means that we didn't use the first 2,000 maps. We only used the other 48,000 maps to calculate the median. And then we also did keep track of 4 different elections, and those elections were like the presidential 2016 election, the Attorney General 2014 election, just to see in each different redistricting plan how many seats each party would have won if they follow that redistricting plan. So again, following the next steps, what we did, so once we found, so this is what our median ended up looking like. It's kind of sparse. There's a lot of entries like missing right now. So like for the ... But as you can tell, this isn't like super like helpful. Like no one can really do anything with this. So next we have a more visual way of looking at it. So this map A was our original starting map for Pennsylvania. So this was Pennsylvania's congressional districts in 2011. And then so our unweighted center here. So this was the map that was most close to this map that came before it when we used the unweighted version. And yep. And then the last one we can see is our weighted version as well. And then, so this was also our distances. This is for the unweighted part, but a little snippet of our distances array. So basically once we had the median, we went back over all the maps and computed the distance between the median and whatever map we were looking at. So we can see the first entry here at like index 0 is our original starting map over here. That was our original starting map. And we can even see that the distances here are like 1,818, which was actually our largest distance. And we can see even in this that the distances do get smaller. Even after the second entry, they get smaller and smaller. And then so the ... And then these are like the last entries in our array. And we can see that there's a huge difference here. And then if I just find the minimum that we got, the minimum distance that we got was 1,489, which lies somewhere in the middle here. But yeah. And so lastly, we also have, remember when we kept track of the election, we also have the number of Democratic Party seats. So our original map was had about 4 Democratic Party seats here, but we can see that this is actually just a giant outlier, and our median map did lie with, or our centroid did lie within the 5 to 6 range, so it was more typical. Yeah. So yeah, that was it. Okay.
Great, thank you.
I also want to thank Brian and Syed for everything, and for Wellesley math department and computer science department.
Great, thank you so much. Do people have any questions? I can ask one if nobody's ready to ask. So what's the weighted versus unweighted? What does that do for you? I didn't quite catch that. I'm sure you said it, but
Yeah, so the unweighted doesn't take into account the population of each VTD entry. So each VTD entry has a varying amount of population. So some of the entries have like 0, and some of the entries have like 2,000. So it doesn't take it into account. It basically views them all as equal. But just like thinking about it, we can see that like obviously a VTD entry that has 2,000 versus should weight more than a VTD entry that has like 1 person in it, basically. So then, yeah.
so the last bar graph that you said 4 Democrats an outlier. It's more like 5 or 6. So is there a way to sort of like say that is it saying that a non-gerrymandered map would typically have 5 or 6 Democrats or something like that? Is that sort of the? Sorry,
Yes.
my kids are screaming over there. But
Yeah. So basically, just to dive a little bit more into like the running the Gerrychain process. So it does, when you run the chain, it does try to equalize those factors. So it does try to take a gerrymandered map and make it not so gerrymandered anymore. So as we ran the chain, we could see in the graph that the number of Democratic Party seats increased, and so I guess that does kind of represent like the non-gerrymandered version.
Cool, great. Anybody else have any other questions? Let me put a plug for a font. It's called Ugly Jerry, and it's made of U.S. districts. Okay, so you can actually, there's a district that looks like every letter of the alphabet is a font that people made with gerrymanders. It's hilarious. I strongly urge you to use it to write to your representatives and demand that your state have an independent districting commission that's not partisan. So anyone else with any questions? Well, thank you all. This brings us to the end of this event. I loved all the talks, and thank you all the students for your hard work. And anyone who has any questions on, again, Institute for Math and Democracy and the work we do and the future plans and how you can get involved, just get in touch with me, and we'll take it from there. Thank you, everyone, again. Much appreciated, all your work. Bye, everyone.